Hello everyone. Today we start the lecture number 3 in our course. Last time we looked more closely at UNEDA lemma, UNEDA embeddings, decided what type of functors we like, why we like them, how to identify type of morphism in a category, and so on. Today we will continue. First we will look at our CAT from last time. It's common categories, group construction, category of elements. Well, why we need them, we will learn a little later. Why they are also as building blocks for all the theory. That will be very clear when we will get to CAD extensions. And I, of course, announce the slogan that everything is a CAD extension of some sort in some way. So we will need them later, but it's good to see them right now and just to practice a little with the category, what functors associated to it, and so on. And then we'll go to a junction. A junction in full detail. Maybe some ways of viewing a junction will be not familiar for you. That's a second. But for the sake of completeness, we should also pay attention to all these things. Okay, so let's start and try to get talking. Let's first look at motivation. I will give two motivational examples. In both examples, we have a category and object A, 1, 2, 0, category. Let's have two objects in this category. Well, I think that's enough. So first example. In category A, we have arrows. We know how to multiply arrows. Some arrows are going in some other direction. That's all. But what's the main thing? That we know that there is a notion of composition. Composition gives us certain equations. How? We can consider a couple of morphisms. Another couple of morphisms. And ask whether the diagram commutes. So whether one way gives us the other. When we are looking at precisely such squares that arise from composition, we are thinking that in a certain way, if we put here x, y objects, here x prime, y prime, here is f prime, let's call this x, this y. That in a certain way, we have a morphism from an arrow f to arrow f prime. Yes, it's a little tricky, but no. You're changing in arrow, both domain and codomain, and getting another arrow. Then you're looking back in your category. So these are diagrams inside your category. What are diagrams? We will talk so maybe on the next lecture. So you're looking at this inside your category, but see that the laws in the category, the law is what that. If you have a morphism from one object to another, you can have a morphism from another in second to third object. That in case when you will attach another diagram to this one, you still can see that you can make composite arrows. Y. And everything behaves similar to the arrows in the usual category, in your base category. Then you are asking yourself, maybe I can organize arrows, morphisms in my category in a way that they themselves will behave as a category. Just because I know that there are squares I can find commutative squares, etc. And how I can do this? So such category will be called arrow category of category A. So A, let's write in this way, is defined to be arrows category of category A. Object are morphisms of A. Then morphisms are commutative squares in composition. It's a composition of, so let's say composition is inherited from composition in A, because we compose vertical arrows when we attach to squares. We compose them using the composition in category. So I will write inherited from more details we'll see in a few minutes. Second example is the following. Then so home functions the same as when I go home functions or representative functions. They are taking a morphism, for instance, from X, Y, morphism from Y, X to Y prime. As I told you yesterday, we are last time, we are changing the domain or codomain. But when we are doing this, one of the ends remains stable, it's fixed. So every time I'm using compound, changing the codomain, for instance, here of some arrow, its domain remains the same. So when I will change another time, by G prime, by double prime, I will have again another angle transformation, but they are both can be composed using composition here. Right. I brought the picture how home functions work this time. Okay. So we can see the same thing going here, but here the beginning is changing. The beginning of every horizontal arrow. Here, the beginning of this arrow is fixed. We can rewrite this diagram in the following way. This will be X, S, y prime. Okay. Similar thing. I can go in opposite direction. So here will be x prime, y, y, y. So right now I'm getting a category where all arrows start from the same object, or another category where all arrows are landing in the same object. Here, all arrows where I would say not wiggling, but for any arrow you could change both where it starts and where it lands. The next step after this, it will be in a little bit, will be the following: that we can twist all the 6 objects by a certain functors. So that we will have not x here, but f, factor f of x, factor f of x prime, factor f of x double prime, and here not y's but something else. So our commutative squares at this will be not inside the category, but will be brought from outer categories inside it. That's the idea of comma category. That you are looking at diagrams of a certain shape in your category and think about these diagrams as being morphisms between certain arrows in this category. So you're considering generalized, I would say, squares, where horizontal arrows you are, by assumption, thinking of them as objects, and vertical, you're thinking about them as morphisms. There is a notion of so-called double categories. It will be once later, or maybe not known. I think it won't fit in our course, where you can also multiply squares this way, taking this. So in the double category, it's a trivial double category. Your objects are the same as these objects. Then you will have vertical cells, vertical one cells, horizontal one cells, and you will have 2 cells filling this. So this the squares will work as building blocks in both directions. It's pretty much what you do in topology when you are gluing homotopes. So either you're continuing homotopy from one function to another, from another there, or either you're gluing. So that's vertical and horizontal composition. We precisely go to this type of categories called double categories. Double categories and 2 categories are very similar, and there is a junction. As I remember, somewhere in this my notebook, it is, I don't remember it. Okay, so that was the motivation. Right now, let's jump immediately to the definition. So definition. So that A, E, C, and G. Pair of functors. Categories are locally small. I'm trying less and less think about the sizes, as I not really. A comma category of F and G is a category F, then arrow down G. Other notations. It's F /G earlier in base Cover G is Y comma K. But this, I never saw it, but I just read. It was like something like this. But this you can verify. But I prefer, honestly, this for me. When I see this, I'm thinking about quotient. I'm thinking about some division, whatever. First, objects. Triple with double P or not? 1P. Okay, thank you. Checking, I like this. Matrix. Object A. Then arrow from FA to GB. F. Here. What I would say is A belongs to A, belongs to OPA. My mistake. My mistake. C. Maybe let's.
Yeah, you may just want to swap B and C.
I'll be smarter. I'll make less corrections. B to B, and this arrow, it's a morphism. Then morphisms are famous. Here I will write another three. Pairs here will be A, B, such that the following diagram have B diagrams. Thank you. And composition. Is it paired? So composition. Oh, well, you never asked me what core identities in those cases, right? So core identities. Identities will be given by here the map identity. So that like identity, identical squares. In this case, identities. Right? Identity. So this thing together will be identity of morphism F. Okay. I want to emphasize 2, 3, and infinitely many times that objects are triples. Even in this case, which we'll describe now in more details, you still have a first object fixed, and it is still element of triple. But it's always the same. Just don't forget it. because once it will get to the point where you want to change something or make some factors out of it, natural transformation between something, etc., then you will think, what components I have and what can I change? Here is your generic example, what you have, not example, definition, situation. And changing factors f and g to be certain, we will get the whole zoo of very funny and interesting animals. Just 3 of them we just saw, but it will be much more. It was a little lazy introduction. Now we will speed up a little more. And definition will be the following: that from category there are 2 factors that are giving you back objects from domain and codomain of your arrows. So it's a factor category A. This part, how do they call it? Domain. Of course, this should be dom sub the triple, not even triple, quintuple, because we have A, B, C, F, and G, or at least pair F, G here. But I will be every time writing dom domain. You can understand. And here it will be codomain. That's not efficient. That's a function. So dom of A and B codomain B is B. You will ask me what gives F is in it, so we have third complex, but if you project on it, will it be object of hidden arrow category? It gives you natural transformation.
Can I ask, so what does domain do to morphisms? So like, what's
Domain of this morphism? I will say that it's A.
Oh no, but the morphisms are diagrams, right? In this case?
Yes, but of course, but domain here, I'm generalizing. So I'm applying domain to objects. And domain of a morphism, here is a pair A, B. It's a pair A, B. So domain will give you first component A.
I see.
That's how it works.
Makes sense.
So if you want a domain, just cut this piece away. If you want codomain, cut this piece away. And if you want a natural transformation, this things away. How we will see it in a little today or maybe other time. This we'll see. But these factors and codomain are crucial. They are insanely important. This is it.
I'm sorry, I just want to ask one more thing.
They serve as an end point, start point, and end point of a path in a space of all paths of a topological space. So it's evaluation at 0 and evaluation at 1 of your path. These things you can see as paths, but don't think that path space of a category looks so simple. No, it is formed not by single arrows. It's formed by, who knows a smart word with a lot of letters Z. Of what is it is made? Of zigzags. The path space of a category is made of zigzags of arrows. But even in this case, it's already good to have in mind that this arrow is as your continuous function from an interval from 0 to 1 to your topological space. And this is an evaluation at 0, this is evaluation at 1. It's a start point, it's end point. Thinking with this analogy will keep you safe. And the path, transformation of path from one to another is a homotopy. And homotopy correspond to natural transformations. That's why I said that here, if I will go to work on it, here will be a natural transformation made out of these things. Example. For example, I need to take my prepared sheet and write you smart words. Over category, or also called slice. It is A over A.
So arrow category itself was an example, right?
Yes, it will be number 3.
Oh, okay, okay. Yeah, yeah.
So what is a roof? By the way, this thing here is called span. When we'll be talking about profunctors, we will talk more about spans and co-spans. Span, yes, or co-roof, because roof is when we are going from C to A and B, going down. Co-roof is when we are. Here is span and opposite co-span. So you can. So this is a span. So what span will be in this case? Here will be A, here is A, here is the trivial category. Here is picking up object A. Number 2, other case. In this case, we have three. It's arrow category. This powerful to identify. This also you could call identity A, comma, and this function. Similar to that. So in this case, you have A, A. If A has an initial moment. Did I tell you what is initial of this terminal object? For me, it's so.
You have not said it.
So I need them to give it. Space. An object works in A. That would be initial. for every x belongs to A, there exists precisely one arrow from initial object to x. Sometimes people call this arrow, if they really need it or want it, also by shrink. Okay. Initial. An object. I don't know how to call it. It's a not letter T, it's perp upside down. Like it's called copper. It's terminal. For y. Let's say so the A. One arrow x to copper. Or that is for definition. If you want to say factorial, this means what? A. This representative factor will do what? Cool. So home from initial to every is one element. Factor. Factors were inclusion of singleton. Now this trivial factor, everything H shrinks. And this is a pickup of object. So in first lecture. So 0 goes to singleton. Identity on 0. There are no other morphisms. So this factors through it. But you can also say that. Yeah, say that. Here, 8. A similar picture holds for. I mean, excellent.
I was thinking there should be some nice way of saying it's using the slice aggregator. Defining the initial and terminal. That's what I was thinking.
Right now, you'll see the connection. So the object is initially if. Is it on if and only if there?
Is it something like an equivalence between the slice category?
Later, you will see how this is related to limits. And all the questions will disappear. There you will understand why it is this way, and you can connect, if you want, with comma categories and statements, comma categories. Still, I will give you some statement right now. I'm not thinking about the if and only if, because it will can get solved as last time it was the skeleton. So I just don't want to go to the cemetery where our time will die. If A has an initial object, then verb, comma A, so cost lines. Is equivalent to it. So the categories are equivalent. Sorry. Well, you can ask me the following: if this holds, is the object initial? This you need to think yourself. I don't know that. Maybe yes. Okay. Wait, so I don't want to spend too much time. on this. Terminal. If A, comma, convert is equivalent to it. Spend applying actually two parameter. Oh. What's another step? I want to emphasize all these categories are arbitrary. All factors are arbitrary. They can be covariant, they be contravariant. How they will be contravariant? Just put them all at some point. So opposite of a common category is a reverse common category of opposite factors. Just you need to switch the order of all arrows here, and you will see that morphism will start from B and will end in A. Yes, I forgot to say here it's F O, here's G O. But yes, you will be right when you will tell me. Here it's B O. Even looking symmetric, it's not symmetric because we are writing from the left to right. No, some people in some countries write in the opposite direction. But I mean, in our convenience, we always start from a certain sign. So even in a pair, there is a first and second component. Even being a pair, where both are equal, but first you name one, only after this you name second. So that's why I needed to write this way. Yes,
I guess we'll run into trouble because of the direction of those arrows. I don't suppose
they will turn. Because you will work in an opposite category of category C only. So they will turn. So that's why I start from category B and B O. However, as you see factors taking off of factor doesn't change anything, as I told you in the lecture one. But taking off of natural transformation change the direction of natural transformation. So off changes the direction of two cells. There is a factor called co, which so little people know, but it is, well, people know more these two categories, which change the direction of one cell. So this thing will get, so what is span? It will go to cospan. There will be two factors launching from C, co. Well, then it will be another thing. But for right now, we have immediately this unit. O. Okay. Then we'll say slice category always has terminal object. And so slice category always has initial object. Who studied a little case theory or a little deeper on algebraic topology knows the notion of classifying space. The classifying space is contractible if your category has initial or terminal object. it's pretty much as if there is a point in your space point, and all paths start from it, and you can collect them back to this point. That's what is to have initial or terminal object for a category. So this category and this one are always contracted. The category is called contractible. If it's classified in space, it's contractible. But this is, we will stay without this drama. Okay? Here will be another small space to show you why. First category, who is this? I never know who is slice, who is co-slice. That slice has terminal object. Let's see how. So suppose it has pair x, then arrow from x to a. The last object is always fixed as a. Then we will, here's arrow f. Then what comes up, it's a yoga of arrows or diagrams or whatever you want, like it's pretty much a part of intersection of homological algebra and categories. Then you will always from one arrow, if you want to keep the beginning, you can take it down and make a trivial square. I mean, why it's trivial? Because, no, it's not actually trivial, it's like, I would say half trivial. Everything works. So who is the terminal object? Identity arrow on object A is a terminal object of slice category. Because every arrow from x to a can be factored as arrow from x to a, from a to a, again a, but identity arrow. So the law of identities in the definition of category is reflected. So this thing gives you here an impact. And always from this object, I mean, that's a separate story for initial one. Don't mess it up. If you have from A to A's, A to Y, to G. So here's an initial object of this category. So because of this diagram, you can say that this category has initial and terminal object. Good. At property 7, I don't know whether we will use it or not, but it's good to know that if a functor from A to B is fully faithful, then it's this functor embeds comma categories in comma, I mean, enlarged. Yeah. So all diagrams are embedded. That's let's take A1, F of A, F of A1 to F A, and then A. A is fixed. And here, Here is FA. Let's call it F2. So this diagram, since it's fully faithful, has complete pre-image in your original schedule. One.
So, sorry, what is your G here? What is your second number?
My second factor is this control factor with a value f. I should write here a. That's my pedagogical mistake because I should mention with a. It's a fixed object. So this diagram gives you this one, but here will be f1 tilde, f2 tilde. Why? Because it's fully faithful. Here I'm using it as full. So for every arrow here, I will find the pre-image. And this is a unique pre-image. Such a story. So this categories are. You can also always write for costlines. Now let's go to remark. And then let's go to category elements. It's with a little jump ahead. Does everyone here know what is a pullback? Everyone? Well, you can skip this moment and in a few lectures again get back to it if you don't know what's pullback. But I will need here pullback of cat. But if you know what is a pullback by universal property, then you can understand what it's meant by pullback of category. So we have factor f. No, let's start from the whole beginning. I have a span. Where am I going to span? I don't know whether it will be correctly called blow up, but probably I will call it blow up. This category C in the following way. So I have C arrow, so arrow category of C. I have functors. Two functors C. This function is what domain? This is a domain. Since my functor f starts in a domain, that's why I write domain down. Arrow. I take category A, here I take F. I take category B here, so G goes down. Then FG can be obtained in a few steps. First of all, here we will take a pullback. Here I will get the pullback. Oh. Back pullback. And also right. Last time right. Degrees. Later I will try to just make wide angle also. Because it's the shape of the diagram. So this is the limit of this diagram of this shape. Push out will be this. This forward. Here will be. Who knows what is homotopy pullback? The homotopy pullback of this thing. So homotopy pullback of a span is a comma category. That's how for homotopy pullback in topology. Here. Wasn't really smart, but good. We can also write C. Comma G. Right there, letter H, that is homotopy pullback. For people who studied algebraic topology, you know about this. The pairs, vibrations, half vibrations, etc. And there are equivalent definitions. One of them is terms of lifting, that this lifting can be also turned to pull back extension to push out, as I remember. So, and you are just switching these diagrams, playing these arrows. The same I will do right now. You can find the same thing in the basic few lectures, first few lectures of algebraic topology, when you talk about vibrations and vibrations.
So sorry, do you mean to say that that the comma category it actually is the pullback? It satisfies the universal property of the pullback in all cases, like
In a category of small of big categories.
no, as in there when you constructed those two pullback squares, you use the arrow category. You don't. That does not have to be the arrow category, right? Like if I just start with a, I mean. I'm just saying that I mean you considered DOM and chord from the arrow category, right? What if you had something like a comma category there itself?
There instead of this,
Yeah, can you still do these pullbacks? Or has it got something to do with starting with that arrow category? That's what I'm asking.
so if you will have wanna here obtain the same, this you mean. So can you obtain arrow category again as in this type? Because it's used here. I used it as a base object, but still can I return it here? Yes, you can. It's obvious how. Here will be identity. Here will be identity. Pullback along identity is the same function.
Yes.
Pullback along identity will be the same function. So here you will get pullback. Here will be C arrow. Here will be C arrow. You will consider objects with pairs of arrows that meet.
I guess what I want.
And this will be again is that thing because you can how it is make it equivalent because of the composition.
So let me put it this way then. What I was asking was, given that situation, you're given functors A and G, we can construct this comma category. Is this the pullback? I mean, does it?
This one, it's not a pullback. It's a homotopy pullback. But here is DOM. Here is called DOM.
Yeah.
It's a homotopy pullback.
Okay, so it does not satisfy the universal property of like what we think in general for pullback.
No, because it's homotopy, so it satisfies this. I can cut all the internal part and I will take the limit of this ladder diagram.
Okay.
So the limit of that ladder diagram satisfies universal property. And this limit is given by f comma g. But this, oh, by the way, this satisfies also certain property. So also called lax limit. So when you fill it with a two cell and consider other fillings bigger with two cells, then all that two cells using the morphism here will factor through this one. Okay. And this two cell, universal one, is given exactly by projection of this component, and that is that natural transformation. What I mentioned 3 times already. Yeah, I think you're boiling.
That makes sense.
I think you're boiling right now because we get very fast. Still, I'm giving you another construction. So right now, I'm trying to give you a flavor how all the things are connected, and at the same thing, you can look in dozen of ways. There's another way to look at this. You have a pair, A and B. Okay, you have just a pair A and B. You have an arrow in this category. You are trying to fit whether the domain codomain of your arrow equal to image of pair AB. Okay, so pair dom codom of F is FA GB, but FA GB is an image of pair AB under the Cartesian product of factors F and G. And this means you have a pullback. It's a category which is a pullback of a certain diagram. Here I'm trying to write this diagram. So I have this H, play cross H, over C. Here I have AD. Here I have F cross G. Here I will have domain codomain. I should write this way to be consistent with module theory and so on. Here will be F. Moment. Here will be our pair, new pair. Well, and here will be projection that now it will be as a function. We are just forgetting that we were coming from different categories. We are just embedding the central squares inside arrow category. A little pullback. Category balance. Category balance. Great. Pointer set. Pointer sets, category set. So you always have X and some star which belongs to X. let's call the star x small. Y is Z. Then what set y? What is the function between point and set? It's a function in set such that this function preserves what? Distinguished point. Under F. So map F. Is given by a function F, where F. Right. But what if we need to pick up object at this point X, not in the set, but in some construction made on this set? For instance, you are trying to pick up some element in a free abelian group on this set. Why not? What if you want to pick up a point in a simplex? Simplex, a point in a simplex. It will be, what is a simplex? It's a contravariant functor from a category. So put category delta to category of sets. So then you are looking at the level where you pick up the distinguished point. And then going, not from so level, it's like a number what you see from elevator, not the whole staging building, okay? Just number of this. But then you will go with this function, push you. That's what you go out of the elevator on the level in the building, on the whole floor. And there in that whole floor, you find the point where you should start. That's how it works with simplicial. All these things are needed, especially this one. This is the simplest one. Why? Not needed, are described by a category of elements. So category of elements is consists of pairs where one first component is an object, the second component is a point in a set which is obtained applying factors to your object. So you can't pick up that in generic category. You can't pick up a point inside object, but you can apply some factor to this object that it will become a set, and then to become the object. I will put up one more. And here will be the definition. Definition. Here's a form. F B is one. The category of F is a category L A integral f. You can L C f. Here it's that depends on course. Also can be just integral of f. Well, S objects will be x belonging to f A, comma A. Where A belongs to category A. So it's a pair object in a category and point or element, distinguished element in an image of this object under factor f. And factor f lands in set, so we can't do this. Morphisms. Here, y belongs to f. Right. Not y, x prime. Right. And morphisms are given by one is f of morphisms f in category A, such that the image of this morphism under your factor brings your distinguished point x to distinguished point x prime. Nothing more. Composition is inherited from category A. Again, I will emphasize that morphism is given just by one morphism in A, such that it brings x to x prime. So I can write it. If x A will go first x prime by f, where f from A that of f like to x prime. Flip. Identities, identity morphisms. They keep everything. Now you can ask me, why I'm being so weird? Why I put first distinguished points and then an object? Why I put first set that point is every culturally advanced person do? Well, for this I have an answer. But I want to bring it back to comma categories. Okay. I just want to do it. So now we will have a couple of ways how to describe category elements. So I have a pair x and a, and belonging to f of a is the same as singleton is being mapped by an arrow called x small to f of a. It is the same by Yoneda that we have a natural transformation. A comma same given by psi. Psi of x. It's 1 to 1. Well, that's size of x is actually the real want to know size of x is f. Square blankets. When you pick up here object B, here will be arrow from F to B, from A to B, it's twisted with F. It's a map between two sets, and then it's this map of two sets is related with coincidence. Therefore, we have two other descriptions of our category of elements. So first one will have star 2 F8 8. What is missing? So, okay, because we need to have three components in common categories. Of course, you can skip it and don't have a mistake about it. But for the purpose of teaching and also deeply understanding, I need to emphasize that there are three components. Of course, this component is fake. You just don't need it. Just forget about it. But if you will skip and forget about it and never will think about it, you will never understand the definition. And there is a remark. Why I'm trying to get here. Here will be primes. Here it's f. F of f. F of a prime. Here's your x. Here's your x prime. Here's your triple. This triple, as you see, everything works. I don't know how perfectly. This triple gives you what? An insight how to write this as a comma category. So we have here a fixed object. So we are working with under category. I mean, under, but this under going not to purely category A, but to the image of category A under F. So this thing, what I will do, I will write the roof. Starting with span. This is a pickup of the single block. This is the function F. And here will be forget the words I write. One second. Just to be more precise, you don't need it's more idea. If I will find it, no, then we'll skip. So here is your homotopy folder. Let's see this is universal level. So category of element L isomorph start. As you see, I am not proving theorems categories theory. I'm just doing some remarks. All category theory, as not all, but most part of it, is a lot of remarks that when you see these things from different standpoint of view. Other ways. And just two other ways. With new data. Testing. Using that, that's what we'll see. We have A. A open. We prime open. F open. We have represent. Then we have here
Should the direction of f of be opposite?
because representative factor, excuse me, the representative factor takes the first component to be contravariant.
I meant there. A op to A prime op, you've called that map f of, does that come from that f or
So
it's
f
a
op,
separate label?
wait, f op from A op to A prime op is a map f from A prime to A.
Okay, so it's not that, that is what I was saying.
So that
Because
no, not that. We can call this remark. One. And here is the remark. As you see here, I need to reverse because these arrows here are getting reversed. So I need to take a photo. If you want to see a span, the span here will look completely different. A op goes to copper sheets by the contravariant. You know that? Covariant or contra, I forgot. Covariant, you know, because it's every object goes to covariant factor. It's not the factors. So factors contravariant, but it brings objects to covariant factor. And here I'm picking up factor F. View. That's all. Not all. This is time. That's easy. My dad was telling me always the story how math books fascinate him. He's a physicist by education. In some math book he opens and saying it's written clearly or obvious, not hard to see, and such formula on a half page. Especially in physics, it's fantastic. I would say, obviously. Yeah, you know, when I was little, I couldn't understand this. But in years, I'm laughing more and more. And that's the difference here. I think you know already more than by thought, by brain. Okay, now example. Oh no, okay. So if A B is a functor f. If f is a functor from A to B, then B f A comma B, this whole set that you will be the as I told you about representative functions, that covariant component goes up, covariant component goes down. Rules from tensor analysis. That B A will be denoted as B. And in general, C from X to Y is C Y. Okay. This all calls it Einstein notation. It's not complete because they haven't said that we will omit multiplication sign if two arguments are in opposite variances, then it's assumed that we are taking n for it, so it will be late. So Einstein notation will just progress. Therefore, B super f is a functor, is assigned to be a functor from category A1 cross set, where pair is B, B, FA. So this thing is a bifunctor. It has two variables. One variable is being weighted by f, another is just home component. Of course, you can write this thing as a composition of Yoneda and FO. So B okay, not today. We just need. I don't want to mess. Fine. Then sub f is defined to be a function from PO cross A, where pair BA goes and then example. Category elements of the following factor. So I'm fixing in my bifunctor one of the variables, the one that is not twisted. And the one that's missing, I'm putting there blank. So where it looks for it. minutes. Sorry. I will mention.
Sorry, what is that? That F underscore mean?
Here it's looking for input from A. So put here A. This is a scale. So I'm putting a blank where you need to put in a number. Twisted arrow kit. When you are trying to learn and prove Quillen's theorem A, you will suddenly see twisted arrow kit. That's one of the first current, whereas not the last. So what is twisted arrow? You are taking F here as prime. And if my map F factors from F prime, then I have arrow from F to F prime. So it looks as that's this arrow. Don't want to mess up. 1 second. No, first. That's a good idea. It's the metric just twisted, but so arrow here. Let's put G here H. So map from F right is given by a pair H. F prime equals H F. Therefore, if I will put here X, Y, prime, Y prime, what I see here, here is map from X O to X prime O, called Geo. And the third component, Y, H, Y prime.
So what are the objects here in this kind?
Triples, X, Y, and arrow from X to Y. But morphisms are different than before. Morphisms before were all going down. Now first is going up. That's why I put here not X but X over.
Okay, you're not defining it as a comma cutting.
I will. But I will to define it as a category of elements, and category of elements is a comma category like. So this is arrow category is A, the isomorphic to category of elements of home. If you want this sentence. All other abbreviations are up to you. Of course, you can put here functors, FG. Also, such things exist. Precisely in this equivalence theorem, here's fun, not here's fun. So first, the image is twisted, a brain image is twisted. by factor. That means that you have here one of these profiles, different profiles. F, upper and lower F. So co-representative and representative spectrum. Okay. So here, this means that not necessarily in all your diagrams arrows are going in one direction. You can make all the directions. Both up, both down, one up, one down. So this is a road with no one line direction. So you can move any way, how much you want. So all diagrams can fit here. Okay, if I would say something right now about gross and net, no, I need to say about gross and net construction. Sure, need to be educated. So I need to tell you about gross and net construction and again running. Maybe we'll make some sometimes additional class because the schedule is so full, like so many things. Okay. Let me have a function F. It goes from category A to a category of all small categories. I change set to cat. Meow, meow, meow. I need to go to cat. Then, what will I do? I will immediately describe to you how the thing should look in proper way. Otherwise, you will be a little confused. But first picture. My idea is the following: that my points, distinguished points in objects, are not necessary coinciding when we move one to one. There can be a shift. Okay. But you can still connect. Why the shift happens, you will understand. So consider A. Here is your object A. And to object A, we assign the whole category F of A. And in this category A, this object has category A prime. Here for an object A prime, we have category F of A prime. So this is small category. Objects form a set. This category, not necessarily as you see on the same level, is object X prime. Then suddenly we want to make a morphism. Yeah, F in a category A. It is assigned to a functor. This functor takes object X to F of X. As you see, they do not necessarily coincide. In the case of set, we had no other choice to coincide, because how would we join two elements in one set? There's no connections in the set. The set looks as a bag of rice. You can pick up this small rice thing and not touching the other. So just bag. Category, it more looks as all these rice pieces, they are joined somehow between themselves. So it's not the rice, I don't know what it is. So taking one thing out, it has strings which are called morphemes to other objects. So sets, please, from now on ever understand as discrete categories. So that's categories in which you do not have morphism, only identity morphisms. So category is also something as a set, but there you have connections You can also think about this as a group of people. If all people are completely strangers, they in one group as in a bus, they don't care about each other really, unfortunately. But if all their relatives, I mean, one relative of other has other relatives, not necessarily one to another, but by relativity, they're all relatives. Then if you will try to take somebody from a bus and say, like, you get out of it, then other relative will say, hey, who are you talking to? Okay? That's a difference between set and a category. So in a set, you don't have connections. And you have no other choice just to fit your point. But when you are trying to wiggle out the situation and enrich it, I would say, with the morphisms between the distinguished points, you'll get to Grothendieck deconstruction. So in a Grothendieck deconstruction, the morphism between two different levels is not only mapped between the labels. I could call them labels, this object label, but also between the image in this direction. Image of the distinguished object to another one. Let's call it X prime. No, I don't like how we move. H. But let's you'll ask me what's the composition. That's fine. I can define whatever I want, but it should be a gamma category. Here's double prime. Here's F prime. Then here's F double prime. Here, F prime. Here's my new distinguished object, X double prime. This object also falls down here and becomes F of F prime applied to X prime. This object continues it's falling from the sky. It's like here F of composition now. F prime F of object X. Welcome to reality. And then here will be a morphism, which one? H goes to F. And here's switch term. I don't know if this was making F of prime is a factor, so factor applied to H. And here is H prime. Therefore, what we have, that the morphism from F prime to F going down, bring object X to its image under the composition of two factors, or factor applied to composition of morphism, and then there is this thing which connects them together. So there is such a defined composition. Also, so I will say that Grothendieck construction factor F from A to F is that it can be written are pairs X belongs to F of A and A belongs to A. Right? That's for most time. What's the idea? Why Grothendieck invented this? He was trying to bring different fibers all together. Total metal space. That's it. So you bring in all the fibers that are different or different points. Your sums and sums and sums and what you have over your base all together. So you can think also about this. All categories are just laying on the whole. I don't know what. So here, I will ask the people if they are waiting. I think in 15 minutes we'll finish, okay?
Actually, I think I'll, sorry.
Okay. I will ask them. And 15 minutes, I think. Are you waiting for a question?
Yeah.
So when is the question?
135.
35. Okay. 135. Last formula. Unfortunately, we didn't get to a junction. And I need to shrink everything next time. Fine. I mean, that was super important things. What I told you today, I mean, yeah, that's rarely so explicitly described. So, growth in the construction.
Just a quick question. Now it's this rotation, right? It's not like it's not the category of elements right now because it's not.
I use different notation just to distinguish. But right now you'll see how they're connected. So, growth in deconstruction of a function that's landed in set and then followed by a function going to cat, which is called discrete. It's the same as category of elements. One by f. You know, my fault is that I'm too much explaining. If I will explain that, I'll get more. But what's the point? I can give you my, printouts. So here I stop. Any questions, please? No questions? Okay, then thank you everyone for attention. Contact me if you have any question. Next time we'll go in a junction and how much we can in limits. I'll try to finish limits as pretty much, so get to the main definition and then just give examples. A junction will be then much quicker. Maybe with not so many details as I want. Otherwise, we won't get in our course to the goal where I need. Or we can make also some additional class. Well, it will save so much energy for everything. Like one additional class. But everybody has their own life, so it's up to you. Thank you again.
Thank you.